Hello and welcome. In this video, I will explore the ATmega328 external interrupts. Introduction. Now let's consider this setup here. So here I have my Arduino Uno with a ATmega328 microcontroller. Now under normal circumstances, the ATmega328 main program will keep this blue LED turned on. So that is the main task or the main program. It keeps this blue LED turned on. Now, when push button A is pressed, the red LED turns on for a second. And when push button B is pressed, the green LED turns on for a second. Now, there are two ways of achieving this. The first method is known as polling, and the second method is known as interrupt. Polling. With the polling method, the microcontroller, the ATmega328, checks the status of these two buttons, button A and button B. So referring to the flow chart here, so the first thing it does is to check button A, and then it asks the question, is button A on? If it's no, it moves on to check button B and ask the question, is button B turned on or pressed rather? And if not, it will repeat checking button A again. Let's assume that this time round that button A is pressed or turned on. It will then turn on the red LED for a second, and then it comes back to the main program, checks button B, and then let's assume again if button B is turned on or pressed, it will then turn on the green LED, and when it finishes that task, it goes back, repeat checking button A, and so on. Now, you may have noticed that there may be a chance, in fact there is a great chance, that button A and button B may not be pressed for a long time. So this is a very inefficient way of achieving the task. Now, interrupts. Now, with the interrupt method, it will look at, in fact, the microcontroller would ignore the two push buttons. Now, when the push button needs attention, and let's assume the push button A is pressed, then only the ATmega328 will look at push button A. So let's refer to this block diagram here. So here we have a main program which, as before, its main task is to keep the blue LED turned on. Now, let's assume also that an interrupt occurs. Now, interrupt can occur anywhere at any time. So let's assume that it occurs here at this point. Now, what the main program will do is to complete the current instruction that is executing. It has to finish that, then branches off to a interrupt service routine, an ISR. Now the ISR is similar to a subroutine. It's a small program that completes a certain task. Now when this ISR is completed, it returns back to the main program. Now with this method, the microcontroller do not need to keep checking the two push buttons. It will only attend to them when it is pressed. Okay, let's consider how does an ATmega328 internal interrupt work. Right, here is the setup. Now in this particular setup, I'm going this arrangement here assumes that I'll be using the internal resistance built into the ATmega328 pins. All right, so that it without showing this, then this does not make much sense. So I have this push button switch connected to the PD2, that is port D bit 2, which is the INT 0 or the interrupt 0. And over here we have the flash program memory. Now I'm going to I have display here the block diagram of the AVR architecture. Now the reason for doing this is to remind us where things are. So I just want to highlight the flash program memory, which is this one here. All right, this block diagram of the flash program memory refers to the flash program memory in the AVR what you call CPU. All right, I just want to everyone to understand where this comes from. Now, the flash program memory contains the main program. Now, when an interrupt occurs, notice that the push button now is red and it's connecting completing the circuit. That will send a signal to the ATmega328. This signal is the interrupt signal. The interrupt signal will then interrupt the execution of the main program. So what it does is now the interrupt signal will cause the main program to complete the current instruction that is executing, and then saves the address of the next instruction onto the stack. It then after that it jumps to location 002H. Now this is the address or the vector address that is attached to the INT0. Now this information is contained in something called an interrupt vector table. I'll come to that later on. Now at this address there will be an instruction that will instruct the CPU to execute the ISR stored in the location in the flash memory. So it will execute that ISR, and then when that ISR is completed, it then returns the control back to the main program. Let's take a closer look at the vector address as mentioned earlier. A quick reminder, when an interrupt occurs on PD2, that is the INT0, it's send a signal to the ATmega328, and that hardware signal will then interrupt the main program, and it sends the control to an address 0002H. So that's where you'll find an instruction that will direct the microcontroller to the ISR. Now 0002H is known as the vector address. Now this address is tied in with INT0. This is being defined in something called the interrupt vector table. Now for every interrupt, as we've seen earlier, there is a fixed address location that contains the address of the ISR, as demonstrated just a few moments ago. For INT0, the interrupt address location would be 0002H. Now, these memory locations are put aside. The whole addresses of the ISR is called the interrupt vector table. All right, so the locations put aside for this addresses, that those memory location is known as the interrupt vector table. So when an interrupt occurs, the microcontroller or the processor jumps to an address location which contains the start address of the appropriate interrupt service routine, the ISR. We've seen that in the earlier examples. Now, here is the interrupt vectors of the ATmega328. Now, I've taken all these information from the datasheet of the ATmega328, and this is table 11-1, reset and interrupt vectors in the ATmega328P. Now, I will be focusing only on the external interrupts. So reset will have an interrupt vector of 0, 0, 0, 0 hexa. Now INT0, as we've seen earlier, is the vector address would be 0, 0, 0, 2 hexa. Now there is a 0 missing in this. I think it's a typo error. Then there is the INT1 that would have an address of 0, 0, 0, 4 hexa. Let's take a closer look at these addresses again. So the reset, as mentioned earlier, the vector address is 0, 0, 0, 0 hexa. INT0, that, as mentioned earlier, that would be 0, 0, 0, 2 hexa. And thirdly is the INT1, that vector address would be 0, 0, 0, 4 hexa. Now, I like to draw your attention to something called the pin change interrupt. Now, this is highlighted here in this red dotted box. Now, pin change interrupt is another form of hardware interrupt. Now, unlike the interrupts that we just mentioned earlier, these pin change interrupt, they are not restricted to specific pins. For example, INT0 is dedicated to PD2, port D bit 2. Now on the Arduino Uno, that is pin 2. Now, so INT0, it is tied in to a very specific pin. Now, for the pin change interrupt, all the pins can be used for pin change interrupt. Any pins on the ports, any ports can be used for the pin change interrupt. They are actually, the pin change interrupts are grouped into ports, and all the pins on the same port create the same pin change interrupt. Now, let me just move on to the next. So this is what I meant. So you can group your pin change interrupt into port B, or you can group them into port D, or you can group the pin change into port C. Now, this is just to make you aware of it. I may in the future do a video on the pin change interrupts. Okay, so far we've covered topics like what is an interrupt, how the ATmega328 interrupt works, and so on. So it's time to take a look at a practical example. Now for this first example, I'm going to use this setup here. So I have an Arduino Uno with pin 11 connected to a blue LED. Now the cathode of the blue LED is connected to a 220 ohm resistor taking down to ground. Then on pin 10 of the Arduino Uno is connected to green LED, and the cathode of the green LED is connected to a 220 ohm resistor, and the other end is connected to ground. Now for the switch here, one end of the switch is push button switch is connected to pin 2, and the other end is connected to the 1K resistor, in turn is connected to ground. Now this arrangement here, I'm making use of the internal pull-up resistor of the ATmega328. Now here is the what you call the wiring diagram on the breadboard. So here we have the blue LED. The cathode is connected to 220 ohm. The anode is connected to pin 11. And don't forget the ground from the Arduino Uno to the breadboard. And then the green LED, the anode is connected to pin 10. And the cathode of the green LED is connected to 220 ohm, taken down to the other end is taken down to the ground. And here is the push button switch arrangement. One end is connected to pin 2. The other end of the switch or push button switch is connected to ground via the 1K resistor. Now, before I get on to the code itself, let's take a look at the steps that is required to program the ATmega328 for an interrupt. So the first thing we need to do is to set up the stack. Then we need to set the INT0 bit, all right, of the external interrupt control register A, the EICRA. The INT0 bit in this register has to be set to a 1. Then next off, we need to enable the external interrupt mask, or the EIMSK. Now, please take note of these acronyms here, because this will be appearing in the code later on. And then the next thing we do is set the global interrupt enable bit, or the I bit, in the status register. That would be the SREG register. And for the requirements, for example, the main program is to keep this blue LED on, and when an interrupt occurs, that will be generated by the push button switch here. That will send an interrupt signal to the Arduino Uno, which will trigger an ISR, or interrupt service routine, that will switch on the green LED on for a short while. So that would be the requirements for this example 1. Okay, so here is the code that I've been talking about. So let's take a look at this part of the code. So the first line here is the include directive that will include this file, then followed by a .csig directive, then followed by the .org directive with an address of 0000 hexa. Now this is the location for the reset, and in this location we have a jump to main instruction. So that would be executed, and it will come down to this part, which is the main portion of the code. Then next comes a .org 0002 hexa. Now this address is the location for the vector location for external interrupt 0, and in this location we have the jump instruction that says jump to this ISR. So the name of the ISR is external ISR 0. Now this can be any other name, it's entirely up to you. I've chosen to call it external ISR 0. Now this part here is to set up the stack. Remember, one of the steps in setting up the ATmega328 for interrupt is to first of all set up the stack. And here you see this RAM end. Now RAM end is defined in the include file. Now this is the last address in the SRAM in the AVR CPU. Now here this RAM N is a 16-bit address. So what it does is this two instruction here will split the upper 8 bits, the high byte, with this function, the high function, and then copy that into R20. And then from R20, you copy it to the stack pointer high byte. Then here we copy the low byte of the address to R20, and then from R20 we copy into the stack pointer low byte. So this 4 instruction will set up the stack. So next comes the setup for the external interrupt control register A. So we load 02. 02 is the hex code to make the INT0 into a falling edge triggered. All right, so you use this code, hex code here, copy that into R20. From R20, we copy this to the EICRA, which is the external interrupt control register A. So we use the STS instruction to do that. That is, STS is the store direct to data space instruction. Now this instruction has been explained in my previous video. Next, we need to enable the INT0. So we need this binary code 0000001, that is hexa01. Copy that into R20. From R20, we copied it out into the external interrupt mask, the EIMSK. And then here we enable the global interrupt I at the I bit. So we use the SEI instruction. Now more of the SEI instruction later. Now come to this point here, we have the SPI port D, 2, that would activate the bit 2 in port D. Remember I mentioned that I'm making use of the internal pull-up resistor of the AVR pins. Now each of the AVR pin in the each of the pin in the AVR CPU has an internal pull-up. So to activate it, we need to set it to our logic 1. So this is what I'm doing here. So activate that. Then these 2 instructions here should be familiar with those who have been following my video. This is to set port B direction register to output mode. So we set port B to output mode with these 2 instructions. Now coming to these 2 instructions here, we basically set port B bit 3 that is connected to the blue LED, that would then switch on the blue LED, and here the jump instruction basically will repeat it. So these 2 instructions will keep the blue LED on. Okay, so let's take a look at the interrupt service routine, the ISR. Now the name of this ISR, as mentioned earlier, I've given it an external ISR0. Now as mentioned earlier, you can name this any other name, right? For now it's external ISR0. So the first line here basically copy the contents, the byte at port B to R16. And then when we come to this part, these 2 instructions basically we do an exclusive OR or XOR here to toggle bit 3 of port B. So that would be in binary 000000100. Translate that to the hex code is 04 hexa. Copy this into R17, and then we carry it out an XOR with the contents of R16 and R17. The result of the XOR or exclusive OR would be stored in R16. Now these 2 lines here basically will toggle the LED, which is the green LED. No, sorry. Yeah, it is the green LED on port B, bit 3. So if it's a 0, it would turn that into a 1. If it's a 1, it would turn it into a 0. And then output that result to port B. And then the final instruction in the interrupt service routine, in fact, the last instruction in any ISR routine is the RETI, that is return from interrupt. This instruction will return the control back to the main program. Okay, so much for the code. Before I go any further, there are a few things I would like to clarify before moving to the code demonstration. Now, I'm going to use information from the datasheet of the ATmega328P. Now, this datasheet, you can download it from this link here. I have actually provided the link in the description, and I highly recommend you download the datasheet. It's very useful. Now, I'm going to use this information from the datasheet to explain the external interrupt control register A, or the EICRA. Remember that acronym? We have covered that earlier. And then I need to also explain the external interrupt mask, or the EIMSK, and also the status register, the SREG. Okay, first off, let's take a look at the EICRA, or the External Interrupt Control Register A, EICRA. Now, this is the information that I've taken out from the datasheet from section 12.2.1. I've extracted that part of the datasheet here. So let's take a look at it. So this is the register is an 8-bit register, and what we're interested in it is 4 bits here: 0, 1, 2, and 3. Now, bit 0, 1, and bit 0 and bit 1 is known as the ISC00, and bit 1 is known as the ISC01. Now, ISC stands for Interrupt Sense Control, and the description of these bits are given here in table 12-2. Now, there are 4 ways of 4 control that we can have, and I'm only interested in this control here, where we need to set ISC00 to logic 0 and ISC01 to logic 1. Then this will give us a falling edge of the INT0 to generate an interrupt request. Because the reason for doing that, because in the first demonstration, or the first example, I'll be using the INT0. Now, in section 12.2.2, we have the EIMSK, or the External Interrupt Mask Register. Again, this is an 8-bit register. There are only 2 bits that we should concern ourselves with, that is bit 0 and bit 1. If you look at bit 0, that is the INT0, and bit 1 is the INT1. Now, when INT0 is set to a 1, we set to a 1, then we will enable the external pin for interrupt. All right, so for this code that we're using, I'll be using the INT0, and this is pin 2 on the Arduino Uno. And this is the INT1. I'll be using this one in the second example later on in the video. Now, the next thing that I want to clarify is remember there's an instruction in the code that says SEI. That stands for set enable interrupt. Now that comes from the status register or the SREG. Now the SREG or the status register is an 8-bit register. Each bit has a particular specific function. I will not go into that here. What I'm interested is this most significant bit here. This is the I bit or the interrupt bit. So when we execute this instruction, this is taken up from our code. So SEI is a standalone instruction with no operand. When you execute this instruction, you will then set this bit to a 1, and that would enable the interrupt. It's only when you enable the interrupt that the instruction following the SEI will be executed. This is not taken up from the datasheet. This is taken from another set of instruction. That is the AVR instruction set manual. Here's the link for that document. Again, I've included this link in the description. Demonstration 1. Okay, so we're now in the ATmega Studio 7. So I uploaded the code here. Let us quickly go through this. So we have the include directive here, the .csec directive, the .org 0000 hexa. This is the vector address for reset, and then we have in that location the jump to main instruction, so that comes down here. Before we do that, then there's the .org 0002 hexa. That's the vector address for external interrupt 0, and there we have an instruction that says jump to external ISR 0. Then we have the setup, the stack here. Then we have the enable the external interrupt control register A, making the INT 0 to do a falling edge trigger. Then we have a enable interrupt INT 0 here using the external interrupt mask. Then we set the I bit to enable the global interrupt. Here, this instruction will activate the internal resistor for port D bit 2. Then this will set up port B data direction for output port. Switch on the LED connected to bit 3 for port B. That's the blue LED. So that will set it on all the time. Then finally, this is the internal ISR 0 ISR routine. So this would toggle port B bit 2, which is the green LED that you will see later on. So this part here will do the toggle, and then here this instruction will get it back to the main program here. So let's now build the solution, and we have no errors, successful compilation. Now let us now try to look at the here's my setup. So I would zoom in here, close up, and go to tools, program it. Yep, it's all right. So the blue LED is switched on. So if I were to interrupt the program by pressing this push button, there's a switch bounce problem here. Yep, that turns it on, turns it off. Let's try again. On, off, on, off. Again, switch bounce problem, and it's off again. And this blue LED is on all the time because that's the function of the main program. All right, so this is the end of this demonstration. Okay, let's take a look at another example. I'm going to call this example 2. And here is the setup for example 2. So I have an Arduino Uno with a blue LED connected to pin 11, a red LED connected to pin 6, and a green LED connected to pin 7. Now there are two push button switch here. This one here is connected to pin 3, and this other push button is connected to pin 2. Now the arrangement here assume that I'm using the internal pull-up resistor in the ATmega328. Right, here is the wiring diagram. Let me just briefly go over it. So the blue LED is connected to pin 11, then the red LED is connected to pin 6, the green LED is connected to pin 7. Push button A is connected to pin 2, and push button B is connected to pin 3. So this is the wiring diagram. Now, these are the requirements for example 2. So the main program will blink the blue LED continuously. Then if push button A is activated or push button A here, then the green LED will toggle, meaning if it's on, then it will be off. And then if you press it again, if it's off, it will turn on. So it toggles it. Similarly, for push button B, it toggles the red LED. So these are the requirements for example 2. Okay, so this is the program or the code for this particular demonstration. And this program is actually almost identical to the earlier program, except for a few additions and modifications. So this is, let's take a look at this one here. So as usual, we will include this file. All right, and then we have the .csec directive. Then we have the .org, which have an address of 0000 hexa. Remember, this is the vector address for the reset, and that this location will have a instruction here that says jump to main, so which is this part here. Then followed by a .org 0002 hexa is the vector address for the external interrupt 0. And then at that location, we'll find a jump instruction to a ISR called external ISR 0. Now these two lines here is virtually identical to the previous example. Then the addition here is the .org 0004 hexa. This is the vector address for external interrupt 1. And here we have an instruction that says jump to external ISR 1. So this is the addition or modification to the previous code. Then we come to this part. Remember to program the ATmega328 for interrupt. So the first thing we need to do is to set up the stack. Again, this is identical to the previous video. So next we need to make INT0 and INT1 set them to a falling edge. So with that, we need to make use of the external interrupt control register register A, and then we need to copy this value 0A hexa, translate that to binary. That would be 0000 1010. Now this last 4 bits here will set the interrupt, what do you call, sense control, the ISC, the 4 ISC bits related to INT0 and INT1. You need to refer back to the datasheet or to the previous portion, previous code. You see the details there. Then next up, we need to enable INT0 and INT1. Now, that we need to make use of the external interrupt mask. So we need to put in this binary value 0, 0, 0, 0, 0, 0, 1, 1. That translate that to hexa is 0, 3. All right, so this will then enable these 2 interrupts. Next, we have the SEI instruction. Basically, this will enable the global interrupt by setting the I bit. This I bit can be found in the status register, as mentioned earlier in my earlier code that we did for example 1. Then the next 2 instruction, which is this 2, right? This 2 SBI will set up this port D bit 2 and port D bit 3, activate the pull-up internal resistor. All right, this will set the internal resistor for these 2 bits to activate it. Sorry. Then this portion here basically will blink the LED connected to this port B bit 3. That is the blue LED on the breadboard, and in between there is a call delay to slow down the blinking rate so that we can see it. And here is the delay subroutine that we mentioned earlier in a few moments ago. Now the details of this delay subroutine can be found in my previous video, that is video 58, blinking an LED using the ATmega328 assembly language. Now I've included this link in the description below. Please check it out if you want to understand this loop. Then finally we come to this 2 ISR that we mentioned earlier. So this is the internal ISR 0. That's the name of this ISR, and it's identical to the previous code that we've seen, except that this time I'm going to blink to toggle the LED connected to port D bit 6. This is the red LED, and this to toggle it, these are the 2 instructions that would do the toggling part. Then this part here is virtually identical to this, except we are using bit 7 for the green LED. Again, this is the part that toggles the green LED. All right, so if you look at it carefully, it's identical except for the bits that are used to to toggle the LEDs. Demonstration 2. Okay, so we're in the ATmel Studio 7. So I've uploaded the code here. Just let us quickly just go through this. So I have the .c seg file here, then the .org for the location for the reset, and then the external interrupt 0 here, and then the .org for external interrupt 1. Then we have the setup, the stack here, enable external interrupt control register A, enable the external mask, interrupt mask. Then finally the I bit, enable the I bit, the global interrupt. Then we set up the or activate rather the pull-up resistors. Then this portion here is to blink the blue LED. So we set it on here, delay, then switch it off, then delay. And then here is the delay subroutine. And then these are the two ISR. So this one will toggle, this ISR here will, this ISR will toggle the red LED. And then this here will toggle the green LED. So let me just upload it to the, what do you call, let me just see. Yeah, let me just upload this, or rather, let's just build it first. So we have no errors, we're successful. Then we go to this part here. Before we do that, let me just see if I can. All right, okay, so we have here the, you can see the board here. So let me just upload the code. Here it's uploading, and you got the blue LED blinking. So this one here should rather toggle the red LED, right? It's on. I'll press it again, it goes off. So it toggles the red LED. Let's do it again. Oh, there's some bounce problem here. All right, so it's on and it's off. So that earlier on-off effect of this red LED is due to the bounce of the switch. That is a different problem. I'll probably make a video on how to debounce switches later on. Now this switch here should toggle the green LED. Again, this bounce problem is quite bad. All right, so now it's on, it's off. Let's try it again. On, off. So that's not too bad. So this is the blue LED. That's the main program flashing it, blinking it rather. And so that's it for this particular demonstration. Okay, that's it for this video. I hope you have found this video useful. I have also included the code that I've used in this video in the link in the description. Thank you for watching, and I'll see you in the next video. Bye!